More than 220 million iPhones are sold each year, according to Statista.
Slowing things down.
iPhone 17, iPhone Air.
That single product makes up over half of Apple's global revenue. Behind each phone is a hidden network of nearly 200 companies across 30 countries. Tiny parts travel thousands of miles before they meet on the same assembly line. What begins as sand in a remote mine eventually turns into the sleek device inside your pocket. The iPhone 17 is not just a phone. It is a global project where silicon from the United States or Australia, glass from South Korea, and batteries from China all come together. Today, we follow that journey step by step. The iPhone made its debut in 2007, when Steve Jobs introduced it as 3 devices in one: a music player, a phone, and an internet communicator. That launch changed how people in America and across the world use technology every day.
So I've got a camera here so you can see what I'm doing with my finger for a few seconds.
Before the iPhone, most phones had physical keyboards. After 2007, touchscreens became the new standard. What many do not realize is that Apple designs the iPhone, but depends on a worldwide supply chain to build it. Millions of workers and hundreds of factories contribute to one device. So where does this journey truly begin? The journey of the iPhone begins with silicon, one of the most common elements on Earth. The raw material is silica sand, often mined in Australia or the United States. These grains are shipped to smelting plants in Japan or Korea, where extreme heat transforms them into solid cylinders called ingots. Each ingot is sliced into thin wafers, polished until their surfaces are as smooth as glass. At Taiwan Semiconductor Manufacturing Company, or TSMC, the real brain of the iPhone takes shape. Inside clean rooms where the air is filtered thousands of times per hour, engineers use photolithography to carve patterns onto the wafers. Ultraviolet light etches billions of transistors, each smaller than a virus, with precision measured at just 3 nanometers. The process takes weeks, and every stage is monitored by machines costing billions of dollars. From a simple grain of sand, a chip is born that can process trillions of calculations each second. But the iPhone needs more than a brain. It also needs eyes. So where does the next part of this journey take us? While chips are being made in Taiwan, factories in South Korea prepare the iPhone's display. At Samsung Display and LG, organic materials are sprayed onto sheets of ultra-pure glass. This creates the layers of an OLED screen, capable of producing vivid colors and deep blacks. Each screen is examined through more than 100 tests. Machines check brightness and color accuracy under different lighting conditions. Other systems test touch responsiveness, power consumption, and scratch resistance. A single sheet of glass can hold dozens of displays, which are cut, polished, and prepared for shipment to assembly plants. Workers in protective suits handle each unit to prevent dust from entering. The display gives the iPhone its window to the digital world. yet the device still lacks the ability to capture images. How does the camera come together? In Japan, Sony produces the image sensors that allow the iPhone to see. These sensors contain millions of light-sensitive pixels, each designed to capture fine detail. Under electron microscopes, engineers check every sensor for defects too small for the human eye to detect. The sensors are then sent to China, where lenses from companies like Largan and Genius are mounted. Once complete, the modules are tested under different light levels, from bright daylight to near darkness. The secret of the iPhone camera is not only hardware. In Apple's research centers in the United States, algorithms are developed to process every image. When you tap the shutter button, complex software instantly adjusts focus, exposure, and color balance. For many people, the iPhone camera has replaced traditional cameras in everyday life. But what about power? How is this device kept alive for hours of use? In factories across China and Korea, lithium polymer cells are molded into the slim batteries that power the iPhone. The cells are layered, pressed under heat, and wrapped in insulating material. Each unit undergoes up to 1,000 charge and discharge cycles to confirm safety and durability. Machines measure temperature and voltage during every test. Memory chips are just as vital. NAND flash and RAM are produced by suppliers such as SK Hynix and Qualcomm. These chips are tested for speed, endurance, and power efficiency. A memory failure can crash an entire phone, so defective chips are immediately discarded. Together, the battery and memory form the beating heart of the device. Without them, the iPhone could not store photos or run apps. Without the battery, it would not even turn on. With the inside prepared, the phone now needs protection. So how is the strong yet light outer shell produced? In China and India, aluminum blocks are cut with lasers to form the iPhone's outer frame. Each piece is anodized to create color, then polished at the nanoscale. The process produces a surface that feels smooth to the touch while resisting scratches. Both machines and human inspectors check every frame for even the smallest defect. All components then travel to Foxconn's massive factory in Zhengzhou, often called iPhone City. The motherboard is placed first, followed by the battery, camera modules, and screen. Once complete, the phones undergo water resistance tests, drop tests, and network checks. Only those that pass every stage are packed into boxes with serial codes and eco-friendly wrapping. And with that, the iPhone's journey is complete. But which part of this process surprised you the most? A modern CPU can contain more than 100 billion transistors, each one smaller than a grain of dust. According to Intel, building a single advanced chip can take months and require machines that cost over $150 million each. The process uses extreme ultraviolet light, chemicals so pure they can corrode steel, and clean rooms where a single speck of dust could destroy an entire wafer. From laptops to airplanes, this tiny square of silicon powers almost every machine we touch. What looks simple from the outside is in fact one of the most complex industrial processes in the world. Billions of switches turn on and off each second inside this chip, directing music, video, and code. But how does a handful of sand transform into the brain of your computer? Today, we open the doors of chip factories to find out. The first commercial CPU was the Intel 4004, released in 1971. It held just 2,300 transistors and was designed to power a pocket calculator. In only 5 decades, that number has grown to more than 100 billion, turning the CPU into the true brain of modern life. From personal computers in the 1980s to smartphones in the 2000s, every digital revolution began with a chip. What few people know is that the design comes from the United States, but production spans factories across Asia and Europe. So how do chip makers turn sand into a working CPU? The CPU begins as ordinary sand rich in silica. This sand is melted at more than 2,500 degrees Fahrenheit in special furnaces to create ingots of pure silicon. Each ingot is a shiny cylinder, sometimes more than a meter long. Saws cut the cylinder into thin discs called wafers. Each wafer is then polished until its surface is mirror smooth. Inside chip plants, known as fabs, the wafers become the base for billions of transistors. Every step happens in a clean room where workers wear full suits to keep out dust. A single particle could destroy dozens of chips. One wafer may carry hundreds of future processors, lined up in rows like tiny city blocks. From this plain disk, the foundation of digital intelligence is prepared. But a blank wafer cannot think. It still needs patterns carved into its surface. So how do engineers draw circuits smaller than a virus onto solid silicon? The next stage is photolithography, a process that works like printing photographs with light. A wafer is coated with a chemical film called photoresist. Then a machine called a stepper projects patterns onto the surface using extreme ultraviolet light. These patterns represent the wiring of billions of transistors. Each flash of light creates lines only a few nanometers wide. To compare, a human hair is about 80,000 nanometers thick. The wafer is exposed again and again, with different masks for each layer of the circuit. Modern processors may require more than 70 layers, stacked one on top of another. The precision is extreme. Machines cost over $150 million each, and they must stay perfectly aligned. Even the vibration of a passing truck outside the factory could ruin the pattern. At this point, the map of a CPU is set on the wafer. But the pattern is only lines of light and chemicals. How are those lines turned into real transistors? Etching removes material to carve out the shapes defined by the photolithography process. Plasma gases are used to burn away the unwanted silicon, leaving trenches only a few atoms wide. Next comes doping, when certain chemicals are added to the surface. These change the electrical properties of the silicon, turning plain material into semiconductors that can control current. Each transistor has three parts: a source, a gate, and a drain. Billions of these are repeated across the wafer, each one acting like a tiny switch that can turn on or off. When connected together, they can process logic and store information. The process takes weeks, with wafers moving through hundreds of machines. Robots transport them in sealed pods along overhead tracks. The entire flow is automated to prevent contamination. At the end of this step, the wafer carries billions of working transistors. But they are not yet connected into a functioning CPU. How do these tiny switches become an integrated circuit? Now engineers add the wiring that links billions of transistors into one system. Thin films of copper are deposited across the wafer, then etched into narrow paths. These wires are smaller than a strand of spider silk, yet they carry electric signals at gigahertz speeds. Several layers of metal are added, separated by insulating material, creating a vertical highway of connections. After each layer is formed, the wafer must be polished flat. A process called chemical mechanical polishing uses slurry and rotating pads to grind the surface smooth. This ensures that the next layer can be placed without defects. A modern CPU may have more than a dozen metal layers, stacked like a microscopic skyscraper. At this stage, the wafer looks like a shimmering disk with patterns covering its surface. Each square on the disk is a separate processor waiting to be cut out. The wafer is loaded into probe stations where tiny needles touch each chip. Electrical tests measure speed, power consumption, and stability under stress. Not every chip passes. Some are too slow, others too hot, and many are discarded. The good ones are marked for packaging. Diamond saws slice the wafer into individual dies. Each die is a square only a few millimeters wide. The dies are mounted onto green circuit boards, then sealed inside protective cases. Gold or copper wires connect the die to the package pins, which will later plug into a computer motherboard. Finally, the finished CPUs are tested again under real conditions. They are run at maximum speed, heated, cooled, and checked for errors. Only the best chips leave the factory. From raw sand to a working processor, the journey may take more than 3 months. And that is how the hidden brain of every modern device is born. But what part of this process surprised you most? In 2024, more than 14 million electric cars were sold worldwide, according to the International Energy Agency. That means 1 out of every 5 new cars on Earth now runs on electricity. In the United States alone, sales grew by nearly 40% in a single year. Yet many people forget that electric cars are not new. They ruled the roads more than a century ago, only to disappear when gasoline engines took over. Today, rising fuel prices and concerns about climate change have brought them back. A modern electric car can accelerate from 0 to 60 miles per hour in under 4 seconds. It does this without burning a drop of gas and without releasing exhaust into the air. So how do thousands of battery cells, motors, and wires come together to form a silent machine on wheels? Let's open the factory doors and see. Electric cars first appeared in the late 1800s, and by 1900 they made up nearly 1/3 of all vehicles in the United States. They were quiet, easy to drive, and popular in cities. But gasoline cars soon took the lead with longer range and faster refueling. For most of the 20th century, electric models faded from the roads. Interest returned in the 1990s when concerns about pollution and oil imports grew. Companies like Tesla and Nissan revived the idea with modern batteries and high performance. So how are these new electric cars actually built inside the factory? Production begins with the gearbox, the part that transfers power from the motor to the wheels. Workers bolt brass fittings into the aluminum housing, then add channels for oil circulation. Hydraulic presses insert bearings with precise force, locking them into position. A device called the parking pole is installed, which holds the car in place when it is stopped. Next come the gears. These are helical gears, cut at an angle so they mesh smoothly. Machines check the teeth under magnification to prevent vibration during driving. Each screw is tightened with a torque wrench to a preset value, ensuring no variation between units. The gearbox is the mechanical heart of the car, built to handle thousands of rotations per minute without failure. Once closed and sealed, it is ready to receive the motor that will give it life. But how does electricity become motion inside this machine? The motor begins with 2 key parts, the rotor and the stator. The stator is a ring of copper windings coated with insulating varnish. Robots insert the coils into slots, then apply heat to harden them in place. The rotor, a steel cylinder fitted with permanent magnets, is prepared separately. When combined, these 2 components form an electromagnetic pair. As current flows through the copper windings, magnetic fields push against the rotor magnets, creating torque. This rotation is the force that moves the car. Engineers lower the rotor into the stator using cranes, then secure the assembly with bolts. With the motor attached to the gearbox, the complete drivetrain is lowered into the rear of the car body. Robotic arms align the assembly with the steel subframe, then bolt it tightly into position. Motor mounts are checked for balance because even small misalignments could cause noise during driving. The next step is to connect the axles. Each axle has a joint encased in rubber, designed to flex when the wheels hit bumps. This prevents vibrations from spreading across the car. Suspension parts are temporarily pulled back to allow room for assembly. Once the axles are secure, the suspension is reattached. Every connection is tightened and scanned with ultrasound sensors to confirm strength. At this stage, the car can deliver power to the wheels. But without a battery, the motor cannot run. So how is energy stored and cooled inside the vehicle? The battery is the largest single part of the car. It holds thousands of lithium-ion cells, each the size of a finger. In one pack, there can be over 6,800 cells, grouped into modules. Machines weld them together using lasers, then connect bus bars that distribute current evenly. The finished pack is heavy, often weighing more than 1,000 pounds. Robots lift it under the car floor, slotting it into the chassis. Once in place, cooling lines are connected. Liquid coolant flows around the cells, keeping them at a stable temperature. Without cooling, the battery could overheat and lose capacity. The final piece is the power electronics module. This unit converts direct current from the battery into alternating current for the motor. Workers mount it above the drivetrain, connecting thick orange cables that carry high voltage. Cooling lines are added to protect the electronics from heat. Next, carbon fiber panels are fixed onto the car body. These are strong and lightweight, reducing overall weight while increasing range. Technicians update the car's software, checking that every system communicates correctly. The car is then lowered onto a test track. During testing, the vehicle accelerates silently. Instead of a roar, the motor produces a steady hum. Engineers measure acceleration, braking, and energy use. The car is also tested for safety systems, including crash sensors and stability control. Only after passing these checks is the car cleared for delivery. From raw cells and copper coils to a complete vehicle, the electric car's factory journey is finished. But would you trade the sound of a gas engine for the quiet rush of electricity? From a grain of sand shaped into a processor, to billions of transistors packed inside a CPU, to thousands of battery cells driving an electric car, we have seen how the modern world is built. The iPhone, the CPU, and the electric car look simple in our daily lives, yet each one hides a global journey of machines, workers, and materials moving in perfect rhythm. These stories remind us that every device in our hands, every computer on our desk, and every car on the road is the result of extraordinary precision. At Captain Discovery, our goal is to open those factory doors and let you witness the steps most people never see. If you enjoyed this journey, make sure to subscribe and turn on the bell so you never miss a new episode. Which of these processes amazed you most, and why? Share your thoughts in the comments below.